All right, so this is the solution I promised you. I gave you the answer to that worksheet problem, the kite problem. I posted the answer and told you I would post the full solution. So here's the full solution. Now, we did half of this or a little more than half of this together in class, so I'm not going to fill in the steps. There's algebra steps I'm going to skip, but you should definitely make sure you can get, like if I simplify something or solve an equation for one expression in terms of everything else, make sure you can fill in those steps and it makes sense to you. So we're going to follow the steps on the handout because I recommend that you follow those steps sort of religiously at first until you really internalize the whole process and understand the sort of why you do things in this order. So in that problem, remember we had a kite 100 feet above the ground moving horizontally at a constant speed of 8 feet per second. And the question says, at what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? So it's pretty complicated. I gave you guys a while to figure out the picture. That was probably the most difficult part, drawing the picture and then labeling all of the moving parts, right? Everything that's changing gets a variable. Nothing that's changing gets a number in your picture. So let's sketch the drawing. So one of you came up with this drawing, which was perfect. So this was step 2. The student said we have a triangle, so we have a right triangle. So there's the kite. It's moving horizontally, and the height above the ground is always the same. So it's moving, so it's always 100 feet above the ground, and it's moving that way. So that's it. There's nothing else to label except everything else in this picture is changing, right? So it gets a variable. So that's step 3. Step 3 is to define all your variables and then label everything. So we decided the things that were changing were this distance here. So it says it's moving horizontally at a speed of 8 feet per second. So that distance between where the string is hitting the ground and where the string and the point below where the kite is, that's the distance that's changing at a rate of 8 feet per second. So that rate that we're given is the rate of change of that distance I've just labeled. Let's call it x. And then I said, well, what else in this picture is changing? And somebody said the angle between the horizontal and the string. So this is step 3. And then the other thing, the last thing that's changing is the length of the string. So I call the angle theta, and then the length of string s, because the string is being let out, so that s is changing. So everything in the picture that changes gets a variable, not a number. So we're not putting a 200 in that picture at all until later. In fact, we're not going to put it in that picture. We're going to draw a different picture, which will represent the snapshot of the moment when 200 feet of string had been let out. At that very moment, boom, we're going to draw a picture of what it looks like then. So step 4 was write down what you're asked to find and what you're given. So we're asked to find, and we're not going to write down the rate at which the angle between the string and the horizontal is decreasing. We don't need to write that. That's already written for us. We're going to write it as a derivative. So that rate of change is going to be d theta dt, and at the time when s is 200 feet. That's what we're asked to find. What is the rate of change of that length of string? So that's not the length of string, of the angle at the moment when the length of string is 200 feet. Okay. And then what rate are we given? We're given that dx dt is 8 feet per second. Okay. So now step 5 is to write the equation that relates the quantities that are changing. So I asked you guys to get an equation relating x and theta. And there's a couple different equations you could write down, but some of them also include other changing quantities, which is fine. You just need to have everything just in terms of x and theta. So the equation we all decided to use, or I recommended that we use, I think a student came up with this, and I said, yeah, this one has just a theta and just an x. So it's tan theta equals 100 over x. So that's the one we decided to use. The other one that we came up with is not bad. It was cosine of theta equals x over s. That will work, but you do have to get s in terms of x or theta in order to have just x and just theta in the equation. Okay, so that just takes an extra step to use that equation. So then step 6 is to differentiate everything. So on the left side, we get secant squared theta d theta dt. That's the derivative of tan theta with respect to time. And then on the right side, the derivative of 100 over 100 over x, which is the same as 100 times 1 over x. So that derivative with respect to t is 100 times negative 1 over x squared times dx dt. Remember the chain rule or implicit differentiation. So now, 7, so before we move on to 7, I decided to solve this equation because we're looking for d theta dt. So I want d theta dt by itself on the left and then everything else on the right. So if I want to divide both sides by secant squared theta, that's the same as multiplying both sides by cosine of theta. So when I do that, I get d theta dt is equal to negative 100 times cosine squared theta over x squared times dx dt. So dividing by secant squared is the same as multiplying by cosine squared. All right, so now I can do step 7, which is to start plugging in. Notice that we don't have x, but we can find it. And we don't have the cosine of theta, but we can find it. So what we're going to do is draw that right triangle again, but at the moment when 200 feet of string have been let out. So at the moment when S is exactly 200, our triangle looks like this. So I've got a right triangle. The hypotenuse is 200, and I calculated the base using the Pythagorean theorem, square root of 200 squared minus 100 squared, and I simplified it, and I got 100 times the square root of 3. Okay, just did a little simplifying. Of course, we're not putting that in our calculator because we want an exact answer. And in this one, we're not, even if it said round your answer, you never round until the very end of the problem. So even if I told you to round in this problem, don't do it during your intermediate steps, because then you're just going to get rounding error at the end. You're going to get the wrong answer. It'll just be too much rounding. So now I can start filling in, plugging in. So d theta dt at the time when S is 200. So evaluating it, I'm going to plug in 100 times square root of 3 over 200. That's the cosine. And then 100 times square root of 3 is x, and 8 is dx dt. So don't square those things out. Notice a lot of things just cancel, cancel, cancel. Right? So that 100 times square root of 3 is being squared, but so is the one in the bottom. Boom, those go away. And then you get negative 800 over 40,000, and that simplifies. So it simplifies to negative 1 over 50. And that turns out to be exact, which is negative 0.02 radians per second. So then we want to answer the question that says, at what rate is the angle decreasing? So we don't need to include the minus sign in our answer. We want to, we solved a problem correctly. We got a negative rate of change because we know that angle is getting smaller as that hypotenuse gets longer. The angle is going to get smaller. So that means we're right. We got a negative derivative, which is fine. It's perfect. We didn't make any mistakes. But now we have to answer the question. The way it's phrased, it says it's decreasing, so it's like they've already put the minus sign in there for us. So the answer is the angle is decreasing. We have to use that word unless we have a minus sign at a rate of 0.02 radians per second at the moment when 200 feet of string have been let out. All right, so this is an example of the type of problem that I like. And I think I got this one from our textbook. So do the problems in Newton using that handout, right? Use that handout, follow those steps, number the steps on your notebook. And that's for your future self when you go back and review. This will be not on the next test, but on the third test, this type of problem. So you want to study how you did it, make sure you can tell what your steps were, what order you did things in. And I'm not going to make you number your steps on the exam, but I want you to start out that way so that you understand the process. The important thing is you do not plug in any numbers till after you've differentiated. Also, if you're told to round, you don't do that until the very last step. So everything is going to be exact, exact, exact. If you round square root of 3, for example, and then you round something else again later, you're just going to get further and further away from the answer, and you're going to get it wrong. All right, I'm looking forward to seeing you all tomorrow, and or in the next video.